Good. So good morning, good afternoon, good evening, everyone. My name is Vince Lecour. I'm the president of the International Society for Geomorphometry. And it's my pleasure today to welcome you to our April 1st coffee talk. Um, I'll start with a quick introduction of what the International Society for Geomorphometry is. If Carlos, you can switch the slides for me. Thank you. So we're an international association of researchers and experts that are open for free exchange of knowledge and opinions about various aspects of DM processing and digital relief analysis. Our goal is to improve the understanding of the properties of the land surface as analyzed quantitatively from DEMs and from digital or paper maps. We also want to advance the techniques used in land surface analysis and especially foster international collaboration in the quantitative analysis of the land surface. And our ultimate goal is to facilitate communication between scientists and students, advertise relevant conferences, and make available public domain datasets and scientific papers. So we're trying to have an online presence, but also in person. So we have biannual conferences. The next one will be held in the summer 2027 in the Netherlands. We also host sessions at conferences like the European Geosciences Union, the American Geosciences Union meeting, and others. So we had one recently, or we'll have one soon in Japan where we can meet and talk geomorphometry in between our biannual conference. And we also, for our virtual presence, so we have a website that you're welcome to visit. There's a lot of resources on it. We are present on Instagram. We have a YouTube channel where we post these coffee talks. We also have a Zenodo community where we share data and papers. Um, and these coffee talks that we try to hold every 2 months. Um, you can go to the next slide. Thank you. So, and I would add from the previous slide that we have also a book coming up this year. So a second edition of the geomorphometry book, Concepts, Software, and Applications. So you can be on the lookout for that. So these coffee talks like we're having today, we hold them between our main biannual conferences. The idea is to have informal discussions, exchanges, showcase our research agenda, showcase specific papers, and also answer questions. We usually try to last a maximum of 60 minutes, but we can extend a little bit today since we started late. Usually we have between 15-20 minutes of presentation and then open exchange or discussion, and then a short wrap up. And you can see here that we have people that registered from a little bit everywhere to this coffee talk, and we'll keep promoting these events. Please promote them through your local networks. If somebody sent you the announcement for this one, you can join our mailing list by going on our website and then receive them. And the more the merrier, as we say. Here we are. So thanks, Carlos, for adding that info. Our next conference is confirmed for 2027 in the Netherlands, and we are setting all the details right now. So by the next coffee talk, we'll have all the details, including date and venue. And so we hope to see you there. I think it's going to be a great event. Well, okay. I went ahead earlier. And then, yes, we have our big, what we call the big blue book. So our geomorphometry book, second edition, that should come out in September. We're currently proofing the book. It's over 1,000 pages of geomorphometry. So from the theoretical concepts to examples from different software applications, including GraphGIS, for which is today's topic, and also a bunch of chapters on great applications of geomorphometry and how geomorphometry can be helpful to other disciplines. All right. And comes my introduction of today's speaker. So it's Dr. Corey White from the Center for Geospatial Analytics at NCSU, North Carolina State University. And Corey, I'll let you share your screen and take over. Thanks for being here today.
Actually, can you, here it goes. All right, so slides should be visible.
Yeah, I see it.
All right, well, thank you everybody for being here today. Yeah, today we're going to talk about geomorphometry with grass and take you through a brief tour of the many tools and analysis that are available within the grass ecosystem for processing. All right. So quickly about me. Yes, I'm Corey White. I am a geospatial research scientist at the Center for Geospatial Analytics at NC State. I was leading our effort for this version of the GRASS chapter for the new Geomorphometry book coming out, which I'm excited, very excited for. And yeah, just want to thank all the co-authors for all the work and effort they put into getting this chapter put together. So a little bit about me and how I got involved with GRASS. I first started using GRASS just as a user back in 2009 or 8. And back then, wasn't too heavily involved, but I really started to get involved when I joined the Center for Geospatial Analytics and got involved with the Geo4All lab here at the Center for Geospatial Analytics, and have slowly continued my journey into the GRASS community, serving now as the most recently added GRASS core maintainer out of the 15 of us. All right. So what is GRASS for you, for those of you who are not familiar, or if you just need to catch up? So GRASS has been around for a long time, but what is GRASS today? We like to say that GRASS is a science-backed, community-driven geospatial processing engine. So this means that GRASS is really good at crunching raster data. It's also really good at crunching vector data, time series, and 3D data. But I think the bread and butter is if you need to process a lot of data quickly, that's continuous field grid data, GRASS is a really good option to choose. So it naturally fits very well into geomorphometry and our various workflows. You can see we have over 800 tools, including add-ons, and it's growing every day. So every time we write a new update list, there's something new being added to the mix, which is pretty fun. Pretty fun and hard to always keep up with what's going on in the community. From our project perspective, GRASS is part of the OSGeo Foundation. It's the parent organization that holds GRASS. However, we've recently switched to a new fiscal sponsor, NumFocus, which, as anybody who's working in open source knows, that even though open source is free, it's not free. It does cost some money to maintain and keep up to date. So NumFocus is now handling that side of the governance and community structure for the project. We are also governed by a project steering committee who they meet on a regular basis to discuss kind of where the project is going and kind of bigger decisions such as for example, like adding NumFocus as a fiscal sponsor. GRASS is licensed under GPL 2.0. or later. And if you'd like a big comprehensive list of citations of academic research that's using GRASS, please check out the GRASS Zenodo repository. All right. So good news is if you want to use GRASS, you can, and it's available on every operating system, or you have Windows, Macs, and Linux. You can compile it from source, and it's just getting easier and easier to use. We recently have Conda available, Conda package available for you just to use Conda install, and we also have Docker distributions and kind of your pick for how you'd like to interface with GRASS. So we have everything from going deep into the weeds to the raw C, all the way through the modern approach of just ask your preferred LLM to code something for you, and it can do a pretty decent job. So just depending on where you sit on that spectrum, there is an option available for you. Some pieces that I'm excited about and we'll touch on a little bit more is a lot of our new Jupyter integration. So if you're looking at doing prototyping through notebooks or trying to produce some reproducible workflow, GRASS has really great Jupyter notebook integration for that. All right. So in terms of capabilities, touched on this a little bit already. GRASS has all the standard raster analysis abilities, all of the standard vector, point cloud, and SQL, but then it excels at all of those. So where if you want to do map calculations, it'll do it very quickly, or develop cost surfaces, or do interpolation. These are going to be very quick. But it also then, where it starts to get real interesting, is when we get into more of the advanced methods that are available within GRASS. So we have many different interpolation methods. So we have, as we're about to go through all the geomorphometry methods, I'll just wait on that one, or hydrology, image processing, etc. Okay, so you're trying to use GRASS and you're getting started. It's the same as any other software. You just begin by creating a project. The only unique thing with GRASS, unlike a lot of other spatial software, is that for the project you're working in, you have to clearly define a coordinate reference system right at the beginning. Now, this is, in my opinion, a huge advantage because it's enforcing that all your data is properly properly reprojected into that coordinate system for when you're doing your analysis. So you have to make sure that you're either using a method that does that reprojection for you when you import, or you need to do the reprojection before you bring it into GRASS. So this is different in the sense that we're not doing on-the-fly reprojection, which is what a lot of other software would do. Sometimes this can feel like things are slowed down, but really it's just GRASS, again, is focused on the processing side, not necessarily the instant visualize your data from an overview. So that's kind of where you have a difference there. For bringing data into GRASS, the nice thing is that GRASS is directly integrated with GDAL and PDAL, and can use any of the formats that your version is supporting to bring data and also export data out. We also have some cloud native support for pulling in data through either Stack catalogs or Stack APIs, YODOG, and then of course we have the GRASS's native data format, which you can also use to bring data in and out. Another interesting note is that sometimes when we're working with our data sets, we don't want to, again, duplicate our data. So we have methods for external linking. So you don't have to copy your data into GRASS and then now have your GeoTIFF and now a GRASS native format also stored. So if you don't want to have a copy of a giant file, you can use this R external or V external method to link the data, and then it'll only be pulled when necessary, but without duplicating it. So now for the fun stuff. So with GRASS, there are lots of geomorphometry capabilities within GRASS. And so we're getting started here. It's really just scratching the surface of what all the what tooling is available and what methods are available. So what we're looking at here, obviously, is just the DTM that was produced using one of our interpolation methods from a LiDAR point cloud. So this is using V-surf RST. So that's regularized spline with tension, where you're able to control the tension and smoothing and minimize and maximize distance between points to create really nice interpolated DEM from your data sets. For PDAL, for bringing in point cloud data, additionally, we have RMPDAL and VNPDAL. So RMPDAL will let you go from the point cloud directly into a binned raster product. And there's you can do that using filtering by band or by class. And then there's a variety of statistical methods for the binning process that'll match your predefined spatial resolution. So for our local parameters, again, we have multiple options for how you can generate your slope and aspect and curvatures. Again, using the V-surf RST as part of the interpolation method, that will also generate your slope, aspect, and curvatures for you, and also partial derivatives for additional modeling processes, such as like overland flow processing. Oh, I'm sorry. Then we also have our slope aspect. So this is using 3x3 neighborhood to calculate the slope and aspect and other derivatives. And we also have our param scale, which is using a multi-scale approach for fitting bivariate quadratic polynomials for a given window. Here are some examples from the curvature outputs. I believe now these ones are from V-surf RST. But again, we have many different methods and approaches that you can choose from depending on your application, which is nice because it gives you a good variety of the options which are available. So GRASS also has your landform identification. Here's an example using our geomorphon, where we're using the computer vision-based approach to classify the landforms. Again, geomorphon, you can parameterize it quite a bit to identify features at different scales and for different areas. However, we also have the ability to do landform identification using our param scale and also our valley bottom. SAR prime scale, like I was saying a minute ago, it's using this multi-scale approach to find the features, and our valley bottom is calculating a multi-resolution valley bottom flatness index. So in terms of ray tracing, here is just the one example of the many. We have r.sun, which here we're seeing the winter and solar solstice for our global solar radiation. It's a really powerful and efficient tool for looking at either daily irradiance, global irradiance, calculating shadows, you name it. The other add-ons that we have around here are rsun hourly and rsun daily. So yeah, if you need to look at an hour by hour representation, or if you need to look at a daily representation of your solar irradiation, again, you have multiple options and methods to do this. So you'll have lots of different topographic indices. This is just a very small subset. We have the topographic position index and topographic wetness. So here we have the topographic wetness index, which again, there's an add-on for it, but also with grass, it's just as easy to calculate it using our map calculator, just by writing a simple expression using your flow accumulation and slope. So again, lots of options here. Also, I forgot to mention earlier, when we're looking at the backgrounds here, as part of the ray tracing, we have this is using our sky view as the relief, and here we're using our shaded relief. So we have different ways of presenting our topographic data to make some really nice visualizations and show off the features. So grass has always had a really wide hydrological set of tools, and that tool set just keeps on expanding and expanding. We have lots of activity in that domain. Here we have a couple different methods that we're showing. We have a single flow direction. We have our D8 method, D infinity, multi-flow direction, and a whole suite of different modules for running these different algorithms. Some are optimized. I would say they're all pretty optimized for any size data, but some are more optimized for high resolution, regional to like continental scale type analysis, such as R flow accumulation, where we are. Yeah, these are some of the newer models that are coming out. Shout out to Hide Chow for all the work he's been doing in the hydrology component for grass, where you can really do some massive calculations over some high resolution data. Here, one of grass's, let's say, probably one of the more heavily used add-on libraries is r.stream. There's a whole variety of different modules that are attached to this package. Here we're looking at the outputs from r.stream extract and our stream order. So we are going from our base stream extraction. And then here we're looking at our Staller and Horton stream orders. And you can also there see the basins overlaid onto the topography. We have another new module where it's now easier to run the height above nearest drainage method where you can calculate inundation using using the hand method. So this is nice because it simplifies the method and gives you spatial temporal output. So if you'd like to do inundation animation, it's really easy to just quickly create that and experiment with different flood depth scenarios. So that's what you're seeing here on the left. And then here on the right, we have the actual height above nearest drainage, where we are looking for the distance from the stream here. Now getting into some more complex modeling, we have our SIMWE models that are prefixed with r.sim. So SIMWE is a 2D water flow simulation based on overland flow differential equations. So here we have an output of a storm event. This is just using uniform rainfall, so just bare minimum parameterization on it to show the overland flow throughout these basins, and this is representing the depth. You also can get outputs of the flow velocity and the particle system as we are flowing through the topography. On the right here, we have our sim terrain output. So this is doing our transport limited erosion and deposition modeling. And so this is using empirical models. So either the Rust 3D or USPD for soil erosion. And this is generally going to be used at watershed to regional scales. And it's also based on the SIMWE model. So another thing that we've been researching and working on are different DEM fusion methods, specifically from our perspective at NC State. We're interested in fusing UAS-based DEM with LiDAR-based DEM to capture changes in topographic change in built environments and understand how that is impacting the hydrology. So here we see an output from our sim water showing us the depth of an area here in Raleigh or in Cary, North Carolina. And what we're going to do here is we'll show we flew a flight, which then of a new development. So this is a new sub-development that went in, performed the fusion using this R patch smooth. And we're able to run the new simulation on top of the data to patch in the elevation change without needing to wait for the next statewide LiDAR flight to capture the change there. So this fusion method is really cool. It uses it's patching together the LiDAR-based and the structure for motion-based DEMs, and it's providing variable smoothing along the edges where there's spatially variable overlap width for how it's doing the smoothing. So when there's higher differences, it can result in larger overlap to help with that smooth transition. We have other modules, R and Blend, which are also available for DEM Fusion. And so again, with our we'll get to it there, with our documentation, you can search by topic to help you find out all the available modules for any given topic that you can think of within GRASS. So this is a very brief tour of some of the modules and capabilities that GRASS has. So let's talk about a little bit more about how can we use GRASS and how can we utilize these tools. So for a lot of people, GRASS has always been thought of as either, well, depending on when you started, it was GRASS is you like to use the shell commands and the command line interface. You can write bash scripts and do some very powerful processing just with that alone. That is still there, and that is also just getting, I think, improving and getting easier and easier to use as the API continues to develop. So when we want to execute a GRASS script, you just have to run GRASS, you set your project. It can also just be a temporary project if you wanted to. And then you can run your commands directly within GRASS. Another exciting thing that we have now is a new Python API. It's the GRASS Tools Python API, which is officially going to be released in 8.5 or 8.6 on
8.5.
in 8.5. And so GRASS Tools is a major improvement on how we were previously utilizing GRASS scripts. It's making the calls feel a little more natural to your Python environment, where you're calling each tool as if it's just a method within the GRASS Python library. So when I think about GRASS and when I'm using GRASS, and I just think of GRASS as a Python library. I mean, I have to have the engine set up. It's similar to how if you're going to be using Postgres or something, you have to have Postgres, but then you can write your code to interface with it. And so that's how I think of it. With GRASS has is handling the big heavy compute processing, but otherwise I'm just importing a Python library and interacting with GRASS there to do my processing and my analysis. The other really great thing with the new tools library is it makes it even easier to go back and forth between any Python library. So if you need data in a GRASS format, or you need it to go jump out into some plotting library, or you need to do some deep learning, you have your data available as a pretty much instantly as a NumPy array that can go back and forth between the GRASS native data format and these interoperable Python data formats that are being used throughout the rest of the ecosystem. The same goes with R. I'm not showing the example for R today, but doing faster, raster, and the R GRASS. And I have a link later on to our tutorial from the Geomorphometry workshop this past summer, where we're showing how to interface with GRASS and R to do stream uncertainty propagation. All right. So we touched on it a little bit at the beginning, but the other really exciting thing with the newer GRASS Python APIs are Grass Jupyter. So this is providing this really powerful interface for interacting and visualizing your data within a computational notebook. So if you're working directly within Jupyter, or you're doing Google Colab, or you're working with Quarto, um, Grass Jupyter makes it so nice just to create really great figures right there in your code without needing any sort of GUI. So all the figures that you've seen here, all of these were just generated using Grass Jupyter. So it's a pretty powerful tool, and it really lets you take advantage of Grass not only as just your computational engine, but also as a pretty powerful cartographic tool when you are able to mix it with the functions that Grass has for cartography, in addition to other plotting libraries like matplotlib or Seaborn or other things like that. All right, so real quick, I'm just going to show, so this is some preliminary work, just of some real world data of using Grass to help with the Hurricane Helene recovery. Hurricane Helene hit the east coast of the United States in 2024, and it was a Category 4 hurricane and caused some massive damage within North Carolina in the mountains. You can see here, this is Swananoa Valley. It's in Buncombe County, North Carolina. It's a very mountainous, forested area that was really not expecting to be this vulnerable to a hurricane event. I think it's one of the big surprising things was that they had the area was pre-saturated before the storm came, and then they had the 1,000-year flood event. So like you see here, they recorded 53 centimeters of rainfall and breaking all their previous flood records by pretty large factors and caused some pretty massive devastation. So where does Grass come into this? So we worked with the Army Corps of Engineers here in North Carolina to quickly process using photogrammetry data from a group called the Civil Air Patrol. And so what they do is it's a volunteer organization that quickly captures aerial reconnaissance of a disaster area after a big event like a hurricane. So it's really our first high resolution data for large amounts of area after the storm. And this is big because at this point, communication for those mountainous areas was down. Transportation through those valleys, some of them were very inaccessible. However, issues arise where this data is not designed for topographic modeling. It's very much designed just to get a quick ortho image for looking and seeing what's going on. So we decided to try to do volumetric change detection, using it to see if we could help with identifying areas that needed help. And then, so yeah, why not LiDAR? Yeah, just wasn't available. So here's an example of the Swananoa Valley, that area that I showed the picture of previously. On the left there, you see that's the overlap from the flight. And here's a drive DTM from that dense point cloud. And here we are resampled at 30 meters. The overall event, it captured 69,000 images, so about 1.4 terabytes of data that we were quickly converting into these DEMs for all the different sites that were flown. So what we've been working on is going from using these data sets that were not designed for that were not really designed for this type of analysis to see how well it works. So you're looking at some preliminary results here. So again, this is we're working on the fine-tuning the details now, but here's an example of a landslide that occurred in the area. You can see it happening here. And then showing how we're going from our topographic change detection to clumping that change and then doing volumetric estimations to kind of help give a sense of how much debris is available for emergency managers. So again, these are ballpark estimations. They're not going to be as accurate as the LiDAR, but it's better information than no information. Here's another example. This is not on the hill slope, but down in the valley where we have lots of sedimentation and you can see scouring of the riverbanks. And here again, from a preliminary result, showing the DM of difference here where we are getting our erosion and deposition. Here we have zooming in, we're looking at this area right over here where we have some interesting, the stream bank fell out and a building ended up in the river. So we're seeing that here. This is also our DSM, our DTM and DSM renderings. And then our 3D view within grass here, showing the stream profile and the landslide through the forested region. So these are the results that are actively still getting worked on. If you look here, you can see that the data is still a little messy, and it's because it's been a challenging co-registration mission between the structure for motion data, and there's no ground control points for the that were flown with these flights. So utilizing the last LiDAR data basically as our ground control with stable features. So actively just in retrospect working on if we had to do this again, how would we improve the photogrammetry and co-registration methods so that we can give to responders these not just the DM of difference, but our confidence intervals on the level of detail of the change. So this is the area that we are still actively improving. As part of this work, started to build a new toolbox for GRASS RDEM, which is including a lot of modules that were just missing from GRASS, in addition to some new ideas that are going to be coming out in the associated paper with this work. So this is a new toolbox to be on the lookout for coming soon. If you are interested in jumping right in, you're super excited to just start using GRASS and you're unfamiliar, I highly recommend trying out the tutorials here. These are relevant to geomorphometry, but also at the same website that we see here, you'll have just your basic introduction to GRASS that'll help you onboard into the processing engine in your preferred environment. So if you're using Windows, we've got you. If we're using Linux, we've got you. I think, do we have an HPC one now?
Not HPC, but there's some parallelization.
There's some other parallelization and a continuing growing list of different tutorials that are in a variety of languages as well, which I don't know the localization of. I don't know those stats off the top of my head. So not everything is just in English as well. Oh, and this is our workshop from the summer, if you're interested. It's the looking at the stream DEM, propagating DEM and SRD stream extraction, although I did not actually mean to click on it. So yeah, that's a really brief overview of GRASS and some of the practical applications that I've been using it for. Thank you to everyone in the GRASS community for doing all this work. So many people that have put their effort into making GRASS what it is, and the community is continuing to grow. So if you're interested in just using GRASS more, or you're working on a project and thinking about where should it live, feel free to join us this summer. There's going to be the next GRASS Community Sprint in San Michele, Italy, July 11th through July 19th. And so we hope to see you there. And yes, thank you.
Hey, are you taking questions? Hello?
And Carlos is muted.
Can you hear me?
I can hear you.
Oh, good. I just have a quick question. On a North Carolina project, there's a lot of erosion. So I've used GRASS tools and some tutorials to look at erosion. But I'm just curious with the scale of the project or where it's currently at. I'm just guessing. Are you trying to like reverse engineer where the erosion is at to where the land is at? I don't know if there's something in a series that you're looking at.
So yeah, for this specific project, it's looking at the difference between the DEMs. Approximating the erosion from that difference. So having them really finely co-register to be able to quantify how much erosion and deposition occurred on the landscape. GRASS also has other modules to simulate erosion, which could be interesting to compare, but we're not using that for this specific project.
Okay. Did you have you said that the state of your data at the point you're looking at it right now, and also the state of the data, it wasn't really set up for topographic studies. So I guess you have more data presently. You're able to fill in because you probably are interested at some point. Although you did say there was no new shots that at some point when you were looking at it.
So there's LiDAR data now, but when the event actually occurred, so this data was used initially, and now we're going through the process of kind of going through it with the fine pick comb and trying to see how good it was in comparison with what the LiDAR data ended to be, because the delay between getting the LiDAR shots and this data was a year, a month. It was a pretty long time before we got LiDAR data post event. So even though this data was not designed for these flights were not designed for topographic photogrammetry, they still served as the best data source at the time for emergency management.
Thanks.
All right, thanks for the question, Iggy. Thanks for the great presentation, Corey. I think you all can hear me well, right? I think that Vince had to go. And also, I'm sorry for all the issues that we have in the start. Zoom was not allowing me to start the meeting, even though Vince created it. And then I had some issues with my camera, which were really, really dumb. But in the end, we're all here. Thank you for these presentations. We're going to open the floor for questions. We're going to stay like, I don't know, maybe 10 or 15 minutes here. You can type your questions in the chat, or you can raise your hands. Please don't use the Q&A because that is somehow new and it's not working really well. We do have one question at the Q&A. It's from Mafuza, and saying that he or she, sorry, I don't know, struggling to use GRASS in QGIS. If you can suggest an easy way of integrating GRASS into QGIS. And before I even give the floor to you, Corey, I might offer a personal perspective. Mafuza, is that you will learn a lot and benefit a lot if you try to use them both side by side, not just GRASS inside QGIS, but if you learn to use them both, you will learn a lot about GRASS, and it's a fantastic tool. But Corey, please, you can.
Yeah, I think that's honestly a good advice, and depending on how you like to interface with the data. So if it's through Q, going through the GUI. So I didn't talk about it today, but that still is an option with GRASS. There's a graphical user interface you can use to get work done. And I also highly recommend trying out the tutorials in the Jupyter notebooks that'll let you explore with minimal amount of coding the different aspects of GRASS. The nice thing is, though, when you're using GRASS outside of Q for your processing, is you have this fine-tuned control over your spatial scale. So your spatial extent and resolution of the processing that you're doing, and you have full access to all the capabilities of GRASS, which I'm forgetting right now off the top of my head, but there are some limitations when you're using GRASS within QGIS that you don't have access to all the tooling.
Yeah.
So you are limited there. So if you're able to do the processing step within GRASS, but then you feel more comfortable going back and doing the cartography or the next step of your analysis within Q, that would be a really nice workflow. Because you can just use that data now within your QGIS workflow, but do the processing.
Yeah.
Is there anything Python related to the study and that's enabled in that study in North Carolina because there's a new Python interface? Because
Yeah.
automated reasons.
Yeah, it's all Python. Well, the analysis is Python. Some of the new modules are C, but you would interface with it like any other GRASS tool. So because they're just new add-ons.
To come back to the QGIS and GRASS thing, it's been my experience that QGIS is generally taking the data and importing it to GRASS before processing by default. I think there's a setting in QGIS to do an R external, which will make things much faster. And things tend to scale much better if you're working in GRASS directly rather than using QGIS to access GRASS. And not all of the options are available in QGIS when calling GRASS as there are in the native GRASS environment. Some of the command options are not available. So there's a real argument for doing some things directly in GRASS versus calling them in QGIS.
Yeah, I agree. I think that people sometimes they don't realize that GRASS has hundreds of modules, and you only have a small subset of that, for point and click access in QGIS. So I really recommend people to try and learn GRASS, and do them side by side. I'm not seeing any questions on the chat. Maybe I can come up with some, because I always have questions for the GRASS team, because thinking on some of the issues that I've seen people facing, I see that some of those are dependency related, like you want to use PDAL and it's not really connecting. So are you guys planning on creating some sort of bundle application like Flatpak images for Linux or something like that?
So Flatpak, not that I'm aware of, but we've really been working hard on getting the Conda package out. So Conda is going to be a big win for a lot of folks. And from our conversations, it's been one of the more highly requested things is to get GRASS Conda package, which will help solve that problem for a lot of users. The other transition that's occurring right now is we're switching to CMake from Make, and that is going also very well. So I think in the future, for different packaging options, it should just be easier to, now that these other components are done, if someone wanted to implement an app image or something, I think it should be a lot easier now with this work that's been done over the past few years.
Great. Yeah. Yeah, I can say that the Conda package works. They work really well. I tried them just last week, and it was great to see everything working and integrated. So it's a great choice for everyone. Oh, we have one in the chat.
Has point clouds been? Oh, I'm sorry.
Go for it, Nikki. I'm reading.
Oh,
yeah.
have point clouds? How long have point clouds been part of the GRASS package?
I don't know how long.
7.2, I think.
7.2.
Yeah, that was on Linux. Didn't come over to Windows until 7.6, I think.
You mean PDAL?
Yeah, Iron Poodle, yeah.
Yeah.
But currently on Windows, you can't use Iron Poodle. Well, it was Iron LiDAR before. But on Mac and Linux, it works quite well.
That goes
It looks
back
like
to-
it's a functional component to a few analysis aspects of GRASS. Just offhand, but just curious.
Yeah, it's mostly, or right now, it's just being used to get data in. So for just pulling in the LiDAR data. I mean, you can use the PDAL pipelines to do processing beforehand, but also once you have the data within GRASS, there's a whole suite of LiDAR tools and applications that you can run there in addition to that.
Great. Yeah, we have a comment from Vacek about the new Python API. He's reminding us that the upcoming 8.5 release works really well with the LLM Gen AI. So the new Python API would be great for those who like to work with the AI tools, right?
Yeah, and I think one of the things from our perspective, I think everybody's still figuring out the new world of LLMs and how they influence big open source projects and their usage. And yeah, I think it's just so new that everybody's figuring it out. But at least my opinion and my hope is that some of these tools will enable researchers who maybe aren't, per se, software engineers, but they're good researchers to say, I wrote this script, it's doing my new model, it's a little messy, can you help me package and clean this so that I can make it an add-on and help get through that part of it, which maybe they're not as confident about, by following basically our the programming best practices. So that's really what we're like with these LLMs. It's training on like this is how you do stuff the grass way. This is how you follow these conventions. And so that's my hope for how it's used. Yeah, but I don't know. We'll see.
And the good thing about the add-ons ecosystem is those tools, some of them have been there for some time, and you can still run them. Like unlike a lot of tools, researchers develop as one-off tools, and then they can't keep up with the maintenance. And so these tools get lost. But if you add these into the GRASS add-ons repository, they receive all these different updates in terms of like Python changes, and so they kind of keep up, and you can still run them. And it also, I think, helps with you can people actually use them for and build on top of them because they are maintained.
Yeah.
So I think that's one of the big advantages of kind of integrating your research into add-ons.
And also for the folks that maybe have anxiety about who haven't done open source contributions and have anxiety about contributing, code review can be scary, but honestly, it is probably the thing that's going to improve you as a developer, and really, it's a good thing, and it only makes everything better. So that's my.
Nice. Yeah. It's interesting that you mentioned about the add-ons, and because one of the complaints that I got sometimes from students is just about that, because in the first step, they got mixed up, and at some points you call it extensions, like g.extensions, and in the website call them add-ons, and a lot of people just like to call them plugins. But that's the easiest part to explain. But then they install the add-ons, and they don't see it. They don't see the tools right up on the interface, let's say. So I'm not just like to ask if there's some movement around that to like integrate the newly installed add-ons to make them show up in the interface like you get with QGIS or any other GIS, because that will make it really easier for the users.
Maybe create a issue for that.
I did a few years ago.
Okay, well then you just like raise it again.
Yeah, it's a good idea, but yeah.
But I do must confess that I haven't really tried to install anything lately and see if there is.
Yeah, I mean,
my issue was answered.
I think that the thing you are describing, the add-ons are there. You can run them. It's just the interface. I think it doesn't update like right away. I think if you open it again, I think it is there. But
Yeah.
I think that's just kind of a minor issue in the interface.
Yeah, you have to restart GRASS before the add-ons show up in the toolbar.
But it's just like probably hasn't been a priority for there are other major things we are trying to work on in terms of the interfaces, that we are adding a lot of JSON outputs for easier parsing.
Can you overlap on that external reference? You mentioned the overlapping function where you could take the result of a raster image and put it on an existing raster image and show the difference. Can you do that over a reference? Or like a large amount of data where you have like a smaller amount of data, but you wanted to do that over a reference? I guess you could. I don't know what the term is of it, like mutable or whatever, editable in a sense, or it's like you can read it.
Are you talking about display or an analysis?
And like an analysis, you have a map, a very large map, or like a dam, and then you went over and grabbed the subdivision by flying over it, and then you wanted to do the difference in the elevation given that you had the new data from the flyover, and you put it over the the other model, and you showed that, but in a separate section you said you could have an external reference for a large amount of data. So if for some reason, if you had that data, can you do that? Can you add that and create do an analysis over that external reference?
Yeah. Which one
You
of
can.
us?
That's good.
Yeah, our external allows you to reference an external GeoTIFF or IMG or whatever image format that Google recognizes, since you have the Google libraries in GRASS. So it will treat that data set that you've externally referenced as being in the GRASS workflow. So you can do any analysis that you want on that external data set, but the results will be by default inside of the GRASS project area. There is an option to do our external out to have things right back out directly to another external format, be GeoTIFF, whatever Google recognizes. But it's quite straightforward to use our external you've worked with large data sets. I mean, I've referenced data sets up to 128 billion pixels without a problem.
And you can still use a computational area.
Oh yeah. Oh yeah.
Great. Yeah, well, we're running about an hour, so if we don't have any more questions.
I had one more thing I wanted to mention real fast that I just want to highlight because I forgot to do it in this presentation, was that the GRASS documentation has had a major overhaul and is a lot cleaner and easier to use and search. And so if you've not checked it out, it's worth taking a look, because it's not going to be on the it's when 8.5 is released, it's going to be unstable, but right now I'm looking at the development branch. So
did you want to share your screen on that?
am I not?
No, you're
Yeah.
not.
Sorry. Thought I was still sharing. Yeah, so
There you go.
yeah, so the whole interface is just a lot cleaner. Sorry, this is a development version I'm in. But yeah, for the tools, you can search through. Get different examples of the different outputs. So yeah, and it's all just a lot more browser friendly. So it's a modernized interface and makes it a lot easier to work with. And if you see an error, you can just click edit this page and make a change.
That really looks nice. Yes. Okay. Just gonna briefly stop your sharing.
All right.
Yes. So we're coming to an end of this coffee talk. Thank you again, Corey, and everyone from the GRASS team. It's really, really nice to have you guys here. Thank you all for joining us. The recording will be available soon in our YouTube channel, so you can also, send to your friends and family so they can learn about GRASS. Send to your grandma. I'm sure she's gonna love it. And yes, keep an eye on our social media. We're gonna probably have some announcements soon for the next coffee talk and for the next conference next year. Hopefully we can see you all there, and also for the book that's coming sometime in this year, in about 3 or 4 months. Thank you all for coming. Thank you all for participating. Bye.
Thank you, everybody.
I
Bye.